that's what a moving average is. Basically just smooths the data. It calculates an average for each point going along. And it's a very important component of any kind of signal processing or geophysics or digital data processing. This idea of a moving average. Which is the smoothest. And this is price versus time, right? But we could also do a moving average smoother over 2 dimensions, right? We could smooth density over x and z. Or in 3 dimensions, we could smooth it over x and y and z. And because gravity has lower resolution the deeper you go, your smoother length is actually going to increase as you go in depth. So this minus 25 to 25 may be very small here. Maybe it's minus 5 to 5 cells. And by the time you get down here, maybe it's 25 cells. All right? So you could take that model, you could smooth it in the computer, you could compute the gravity data, and you'd probably get a very similar result to the idealized model. Okay, any questions on that? All right, we're going to change subjects now, and we're going to start on seismology. And for those of you that are doing geophysics, probably 95% of what people do in geophysics is seismology. For those of you that are in geotechnical engineering, probably 90% of what you do is seismology related. So it's probably the biggest component of what you do. It's what our field experiment is going to be, what our field trip is going to be based on. And it's what I know better than the other stuff. So what is seismology? All right, the simplest explanation is that it's sounding the ground. All right, you basically send sound waves into the ground just like ultrasound. The ground is a little bit different than the air in that the waves that actually go from point to point are more complex. And that's because the ground is a rigid material as opposed to a fluid or a gas like air and water. Seismic is primarily used in oil and gas exploration. That's the biggest budget expenditure for geophysics in the world. It's also used somewhat in mineral exploration. It's used in looking at seismic hazards, slope stability, rippability of rock. It's looked at in environmental and groundwater, basic research, forensics. The applications go on and on. I even used seismology to look for truffles in Belgium, a research project a long time ago. Okay, so we're going to go over some of the theory of this, but mostly what we're going to be looking at are items 1 and 4. Okay, we're going to be focusing on seismic refraction analysis of first arrivals and surface waves. Seismic refraction analysis of first arrivals is used to obtain things like depth to bedrock. It's also used to, in a very cursory way, characterize water table depth. So those are two kind of near-surface applications. Surface waves and dispersion are used to characterize the shear wave velocity profile of soil. So if you want to understand how stable your soil is for designing a building and how it changes with respect to position, that's the typical technique. And the reason we do that is that we don't want to spend the money drilling boreholes everywhere. We want to save money by actually characterizing the rock without having to go and drill a borehole every 10 feet or something like that. So there's a lot of material here, but that's going to be our focus. Okay, we've got lots and lots of different sources of seismic waves in the ground. Obviously, we all know about earthquakes. We know about volcanoes. Just as an aside, does anybody know how a number of the, like Mount Pinatubo in the Philippines, how they actually could predict when the volcano erupted? Well, a volcano, some volcanoes, have essentially tubes of magma. All right? And actually, these are not, they basically go on down to some depth like that. Right? And obviously, when a volcano erupts, the magma comes spewing out like that. So, imagine this tube when this top is open. It's almost like a flute with some end and an open end here. If I would blow on the bottom of the tube, I would get what? I'd get a tone, right? If I blow on a flute, I'd get a tone. And that tone is a resonant frequency. It's basically a sound wave that we hear caused by waves bouncing around in that tube. So what happens if I close the top of the tube? So I put my finger on it. Or what if basically because of crystallization or something like that, the magma actually formed solid and closed the top of the tube? What would happen to the sound wave? Not much, actually. So just imagine there's no rock here. Just imagine that glass tube. Yeah. Remember the half pipe thing where the resonant frequencies of the pipe and how what the fraction n lambda over 2L versus n lambda over 4L for the resonant frequencies. Everybody remember that from Physics 101? Well, that's exactly what's happening here. If this is open, it has a certain resonant frequency. If it's closed, it has a different resonant frequency. So if you have an ear listening to the sounds and you see a change in the resonant frequency, you can say, holy shit, about the blow now. And that's exactly how they predict when volcanoes are going to erupt. By measuring this change in the resonant frequency. We'll get back to resonant frequencies and frequencies in general. Harmonic tremor is what people are looking at a lot in earthquake seismology now. We can have continuous excitation. Wind can cause things. Microseismic wave action actually sends sound waves through the earth that we can detect. What we use in exploration geophysics oftentimes are explosions, either buried or surface. We actually use dynamite to send sound waves into the air. And the reason that we use dynamite is because, one of the reasons anyways, is because it sends a very sharp signal. It goes like that. It's a sharp signal versus time. So if I were to look at the time history of the dynamite signal, I basically see a very short duration signal. I can use a similar thing in the water called an air gun. An air gun basically is a cavitation. It's basically a bubble collapsing, almost like a balloon popping in reverse. So you get a pop. Okay, again, that's a nice short duration signal. We can also use a technique called vibrosides that we talked about first day of class, where we have a mass vibrating up and down on a base plate. I really don't want to go very much similar to chirp radar and the way that bats go on to figure out where they are at night. So, this is what we're going to be doing. Now, a huge component of the class is your, we do grade this. It's basically how do you handle a sledgehammer. Right? So, these are examples of how not to handle. Right? You notice this person here is not faced parallel to the target with his hammer, okay? He's hammering this way with his feet like this. Now that's just a stance issue, all right? We can fix that by teaching you that in class. You're basically supposed to take a plate and your body should be parallel to the target, all right? This is not right, okay? So this guy's making a huge mistake. You get to see right. Easily fixable. This guy has a great profile, right? But what he's done is he's taken the hammer behind